So I want to start off by talking about dividing rational expressions. We got up to this point yesterday in class. I asked you to do these problems today. You have to be clever for today. Let's go over them quickly so that we can move forward. The key is if you are dividing rational expressions, I can turn it into multiplication by inverting the second rational expression. So in this case, I am inverting this one. Okay? So this denominator here becomes the numerator here. Now, the other thing that you had to be made aware of is the fact that you have to know how to factor the sum of two cubes. That's a special factoring that we did U to P. So if you don't know those things, I mean, come on now. Now's the time. We need to be skillful when it comes to factoring. You will see that again in pre-cal and calculus and beyond. Factoring is not going away. All right, so then you have to be clever. Now, at this point, you may have the urge to factor this, but you really don't have to. Why? Because notice, this is exactly the same thing as this. So I don't even have to factor that any further, or if it's not factorable, I don't have to do anything else to it because these are common factors and I can immediately cancel them out. I can reduce this by, dividing each of those by that common factor. Then I also notice that I have this and this the same. So all that's left is this and this. So you have to be clever. In the next one, again, I inverted. So notice that this becomes this. This division becomes multiplication. I factor the numerator. As this. I factor the denominator as this, and then I reduce. I simplify. I look for common factors in the numerator and denominator. In the next example, again, I invert the second fraction and turn the division into a multiplication problem. Hopefully you recall how to factor by grouping. And then at this point, you may have the urge to reduce this since this is the difference of two squares, but let's be clever. If you automatically see a common factor in the numerator denominator, reduce it. You could simplify, you could factor each of those and reduce those separate factors, but quick and easy. Let's be clever. In this example, you had to invert not only the second one, but you had to invert the third one because I see two sets of division. So to turn each of those into multiplication, I had to invert the second and the third fraction. And then factor, reduce by looking for common factors in numerator and denominator. And oh my goodness, this is beautiful. Look how beautiful that turned out to be. Okay? Now, let's talk about adding and subtracting rational expressions. Adding and subtracting rational expressions. Well, rational expressions, they're fractions. And so recall, what do we have to be able to add and subtract fractions? Same denominator, common denominator. So if I have the same oops, I didn't want to do this. Let me go back. And let's go back to the blank ones and let's start from scratch on that. I have to have common denominator. Now, if I look at this first example, I have the same denominator. So all I have to do is perform the operations in the numerator, the corresponding operations. So I have 5x plus 1 minus 4x minus 2. All over my common denominator, x squared plus minus 9. Now I am subtracting every single term in the numerator of my second fraction. So I have to distribute that minus sign. You have to be careful. 5x plus 1 minus 4x plus 2. All over x squared minus 9. Now, what would I do next? Combine like terms. So I have 5x minus 4x gives me what? X. And then with respect to my constants, I have 1 plus 2, which gives me plus 3, all over x squared minus 9. Now, is that simplified? No, because I can factor that denominator. So I have x plus 3 over x plus 3, x minus 3. I see common factors. So what is my final reduced form? Beautiful. Now, recall, if you have different denominators, I have to get a common denominator. Now, you do want to try to find the least common denominator to make the problem a little bit easier, more so than harder. But if worst comes to worst, to get a common denominator, you could just multiply the two denominators together. Okay? So in this case, let's say, I mean, do we have a least common denominator? It's going to be 21, right? So what am I multiplying the first fraction by? 7 over 7, and thank you, because I'm multiplying by 1, so it is 7 over 7, and what am I multiplying the second fraction by? 3 over 3. So my first fraction now becomes 35 over 21 plus 6 over 21. I have a common denominator now, so I can just perform the operation in the numerator. 35 plus 6 gives me 41 all over that common denominator 21. And if I hadn't chosen the least common denominator, I then at this point would have to simplify further. I'm good. So let's talk about how I'm going to perform addition and subtraction when I'm dealing with more interesting rational expressions. So hopefully in the first one, you notice you have a common denominator. So I'm just going to go ahead and, again, on the test, pay attention to the operation. If this was multiplication versus division versus addition, or for that matter, subtraction, I would begin the problem different ways. So in this case, I have x squared plus 4 plus x squared plus 5 all over my common denominator, 2x squared plus 9. Go ahead, let's combine like terms. And what am I going to get? What can let's go through the process. X squared plus x squared gives me 2x squared. 4 plus 5 gives me 9. Over my common denominator, I have like factors, so I can go ahead and reduce this to 1. Now, looking at the next one, well, I can't factor the first denominator. So now let me just rewrite this and let's talk about what we would multiply each of these by. So the first one, I have x plus 2 over 2x minus 3 minus 4 over x plus 3. What am I multiplying the first fraction by? -1.
Oh, never mind.
Oh, I love the real-time thinking. I love it. I love it. That's beautiful. So what am I multiplying each of the fractions by? The first one I multiply by, what is this denominator missing? X plus 3 over x plus 3. What is my second fraction missing? Okay, now looking at this, what am I doing with those? Binomial times a binomial. What do I do? FOIL. So that's going to give me x squared. Can we do it in one step? Plus. Minus. I'm going to just, since I now have a common denominator, can't I just do this? Because they have the same denominator. And then now let's distribute, shall we? And what am I going to get? If I distribute here,
8x minus 12.
So notice how I left this a minus sign here. Now I'm going to distribute. And I'm going to get x squared plus 5x plus 6 minus 8x plus 12 all over my common denominator. I'm not going to multiply those yet because I don't know, maybe something simplified. We see. Now, can I combine those terms in the numerator? What am I going to get? Is there another x squared? No. Am I done?
No.
No, because what can I do? Well, or, I mean, I don't we want to see if I can factor that numerator and maybe get something that reduces with one of those factors in the denominator? Yeah, let's do that. That would be my instinct. Let's factor that. What are the factors?
X minus 6.
Ha!
Wait, hold on. That doesn't work because 18 is positive. Oh.
Oh, 18 is positive. So is there anything I can do to that?
No.
That may be simplified. Imagine that. So addition and subtraction is the same thing, right? As we did with fractions. There's nothing else I can do to that. So be careful. If you can factor, and you can leave the denominator in factored form, I'm okay with that. Now, I'm going to leave these as practice for you. You're going to do these on your own. In the interest of time, I'm going to move forward and talk about the next topic, and we can revisit this if we have time at the end of the class, but I highly recommend that you do these. And you know, if I highly recommend that you do something, you know, it's in your best interest to do them. So let's talk about what's known as a complex rational expression. What is a complex rational expression? Now, you may be thinking, well, complex, does that mean a plus bi or a minus b? No, I'm not talking about complex numbers. I'm talking about complex as in, ooh, complicated. Complex rational expression. A complex rational expression, also known as a complex fraction, contains one or more fractions in either the numerator and or the denominator. So if you notice this very, let's say, bold dividing line, let's look at the numerators and denominators of each of these. In this case, I have, just a little binomial in the numerator, but boy, look at that denominator, rational expression. Or in this example, my denominator is just a nice little linear binomial, but ooh, look at that numerator. And in the last example, look, a rational expression in both the numerator and the denominator. So those are complex fractions. Now, complex fractions, I want you to keep in mind, is just another way to represent division. So I can just rewrite these complex fractions in terms of a division problem, numerator divided by denominator, and then instead of dividing by the denominator, we multiply by the reciprocal of the denominator, and it turns into a beautiful multiplication problem. So this is just, they look complicated, but they're really not. So let's simplify this complex fraction. In the numerator and denominator, I have both rational expressions. So my numerator is just this. So I can rewrite this as x plus 1 over x squared minus 1 divided by the denominator Can everybody see how I turn that complex fraction into division? Numerator divided by denominator. Now what? Invert the second rational expression. So I'm leaving the first one alone. Not touching it. Oops. I'm inverting the second one. And I'm turning this division into multiplication.
Oh, you only have to invert this.
I'm only dividing by the second one.
Oh, yeah.
Right? Now, for heaven's sakes, what would I do next? Yeah, okay. And what do we?
Factor the bottom.
Can we? Thank you.
Denominator.
Let's factor the denominator of the first rational expression, the first fraction. And what would those factors be?
X minus 1.
Mm-hmm.
Dr. P,
Yes.
would the original first fraction not be simplified form?
No, it's not.
Oh,
I don't have to give it to you in simplified form. Why am I going to make it easier on you?
okay, that's a good point.
Okay, what would I do next? Do we see any common factors from numerator to denominator?
Yes.
You bet. X plus 1 and x minus 1. So what does this simplify to?
1
Another X.
Let's set 1 over x. Shall we do another? Okay. So I have x plus 1 over 3 divided by 3x, bless you, plus 3 over 7. What do I do?
you can subtract. Well, first you take this.
I would turn this into multiplication sooner than later, because if you start manipulating either parts of these fractions, you may forget what operation you're doing. So let's get it in the form where we can start working with things, but I know where you're going with this. What do I do next?
Factor out of 3 from the denominator.
Yes. Josh.
Oh, then you can simplify by turning the denominator, or where you just cross off x plus 1 in the denominator and numerator, and then rewrite the fraction as 7 over 9.
I love it. These are fun. Now, there are other ways we can simplify complex fractions. So to simplify a complex fraction, rational expression, I could also multiply both the numerator and denominator by the least common denominator among those numerators and denominators. So I could have instead, what I meant is look for the least common denominator here, which would have been 21, and I'd multiply the numerator and denominator by 21. That would allow me to address those fractions. So let's go ahead and look what I'm talking about in these examples where we don't have x's. Let's just look at them in terms of constants. If I'm looking at each of these, what would be the least common denominator from numerator and denominator? What would the least common denominator be? What are your denominators? 2, right? So my least common denominator is 2. So that means I can multiply this numerator by 2 and this denominator by 2. So what does that entail? That entails distributing that 2 to everything, every single term. So in the numerator, 2 times 5 is 10, plus 2 times a half is what? 1. Do you see how I distributed the 2 to each term in the numerator? Okay, that is divided by, let's go ahead and distribute the 2 to each term in the denominator, and what am I going to get? 6 minus 3. Do you see that? So my numerator is 11, my denominator is 3, and I'm done. No domain restrictions on this, right? Because there's no variables in the denominator. Okay. Again, what would the least common denominator be in this one? 2. I could split it into a division problem, invert the second fraction, and turn it into multiplication, or I could do this. So let's go ahead and multiply every term in the numerator by 2, every term in the denominator by 2, and tell me what I would get. In the numerator, I would get what? 2 minus 3, and in the denominator, I would get 1. So this simplifies to -1 over 1, which is just -1. Again, no restrictions on domains or anything, no variables in the denominator. So let's identify the least common denominator in this next example. What is my least common denominator? X. So I'm multiplying each term in the numerator by x, each term in the denominator by x. Again, I could have turned this into a division problem, but then each of those little binomials, I would have to simplify first. So let's distribute x in the numerator, and what am I going to get when I distribute x in the numerator? Excellent. Anything else I can do?
Plus x squared minus 2.
Oh. Why did I put a... That's a 2. Yes. Anything else? I can't factor the numerator, but yes, I can take out the greatest common factor, 3, leaving the x squared minus 1. Oh, and you know, if I really wanted to, I could then look at that as the difference of 2 squares, couldn't I? But that's not really getting me anything that I can reduce further. So I would take this, I would take this. No, I would like to see this. Sure. Let's go all the way.
Wait, it can't be the difference. One's bottom.
Yes,
No, one's
x
negative.
squared minus 1, so.
This is the difference of 2 squares.
Oh, sorry. I was
Right.
talking about-
Okay. All right, let's talk about the least common denominator in the next one. What is it? Ooh.
1 plus x.
1 plus x. So I'm multiplying this by 1 plus x. And I'm multiplying this by 1 plus x. So here we go. In my numerator, what do I have? I have just 1. In my denominator, remember I am distributing to each. So what do I have? 1 plus x minus 1. Does everybody see that? Okay, I can simplify further to get what? Domain restrictions? Any domain restrictions? X is a real number, but x cannot equal -1 or 0, right? Technically. I can't be -1 from here, making that 0, but I also can't be 0. Okay, let's do another one.
Is it because we can't be 0 because 0 over...
Anything divided by 0 is undefined. Least common denominator in the next one. So for my numerator, what do I have? Okay, well, you know, I am gonna keep it like that because of who knows, maybe down the road I can simplify. Yes, Miles. You are correct. I'm gonna keep it like that. Okay, what about this? If I distribute here, what am I gonna get?
X squared minus 2x.
X squared minus 2x minus 3. What do you want to do next? Let's factor that. We've got some other things that may be going on. If I factor the denominator, what are my factors? Oh, and lo and behold, common factors. So this reduces to x minus 2 over x plus 1. Leaving that as a practice problem for you. Ooh, look, we have to simplify that numerator first and then address that least common denominator. More practice for you here, even with negative exponents. Super exciting. Even more practice with factoring. But I do want to talk about solving linear and rational equations. Solving linear and rational equations. So to solve a rational equation, you're, again, multiplying each term of the equation by the least common denominator in each of the expressions. Doing that allows you to eliminate the denominators completely. It makes your life beautiful. So in this case, if I'm looking for my least common denominator, what would my least common denominator be? Is it 30? Yeah, because 5 times 2 is 10. 2 times, yeah, 30. So I'm going to take each one of those terms and I'm going to multiply each of them by the least common denominator. This is going to allow me to just completely get rid of those denominators.
Would you multiply by 30 or would you multiply 2 6? So you multiply 5 by 6, correct?
I'm sorry? No, I'm multiplying every single term in the equation by the least common denominator. I'm not trying to get it. I'm trying to get a common denominator of 1. So multiplying each term by the least common denominator. Okay, so let's go ahead and simplify. So 5 goes into 5 once. 5 goes into 6 how many times? Oh, 5 goes into 30. How many times? Okay. Do you see what I'm doing?
Oh,
2 goes into 2 once. 2 goes into 30 how many times? 3 goes into 3 once. 3 goes into 30 how many times? So what am I really looking at? I'm looking at 6 times 3x minus 15 times x minus 3 equals 10 times x plus 2. Do you see what I've done?
yes.
I've made this problem so much easier. Now let's distribute, shall we? So what do I get? First term. And then now I'm distributing this minus 15 to each of these. So what do I have? Minus 15x. You tell me. Yes. Equals, distribute. Now, this is just a linear function. Let's get all our x's on one side of the equations. So I have 18x minus 15x minus 10x is what? Okay, equals 20 minus 45, what?
So x equals 25 over 7. There's nothing wrong with that answer. Is there? No. Now you do want to make sure that you're checking for extraneous solutions if need be. So looking at this next example, what would our least common denominator be? Least. 10x. So I'm taking each one of these and I'm multiplying it by 10x. So what is that going to give me? The first term becomes what? 10 equals, beautiful, plus, excellent. So 2x equals -5, which implies x equals -5/2. Any extraneous solutions there? Is there anything that x cannot equal?
0.
X can't equal 0. Right? If this is my least common denominator especially, set that equal to 0. That's going to tell you the values of x that you have to exclude. So do check for extraneous solutions. Looking at the next one, what is the least common denominator?
X squared plus x plus 6.
Okay,
Minus
Minus.
let's factor that denominator. Well, I don't know why you're giving it to me as a trinomial. Factor it and see what the least common denominator is. In some instance, maybe one of these is a factor of this, right? You won't have to multiply the whole thing together. So your least common denominator is in fact x plus 3 and x minus 2. So that is going to imply that x cannot equal what?
3.
That's right. So if you get any of those to be answers, you need to exclude them. They're extraneous. So let's go ahead and multiply every single one of these by the least common denominator. And let's simplify what we can. Let's look at this. Ooh, how exciting is that? Oh, that's lovely. Ooh, wow, fantastic.
Dr. P.
You see all that? So what is that going to leave me with? For the first fraction, what do I have? What does that simplify to?
6x minus 4.
Thank you. Minus what? Where did my little 5 go? Where'd my little 5 go? There we go. It's back. Oops. So that becomes just minus what?
5x.
Minus 15. So while that becomes 5x plus 15, remember I'm subtracting. Are we okay with that? Okay. And then on the right-hand side, I just have, yeah. Lovely linear equation, 6x minus 5x is x. Negative 12 minus a minus 15 becomes, oh wait, negative 12 So this is, hang on, let me just underline this. This becomes x. This becomes, So what is x? Is that valid answer? Yeah, because these were the only restrictions I had. So check for extraneous solutions, right? Do we want to do this? You want to try this one?
No,
We did it.
Oh my gosh. What kind of attitude is that?
a great attitude.
Terrible attitude. Okay, I just want to introduce and remind you, and then we're going to spend the rest of the time doing these problems and we'll go over them. But I just want to give you a brief, before I release you for this weekend, give you a brief reminder of that parent reciprocal function, because we're going to be working with that and graphing some beautiful things next week. But since we start next week on a virtual day, I'd rather refresh your memory now and then get into heavy duty on the virtual day, okay? So as just a refresher, and then we're going to go back and do all the problems that we skipped. As a refresher, remember the parent, when we were building our library of parent functions, if I remember back to the parent reciprocal or rational parent function. The parent function, also known as the reciprocal or rational. This last unit was polynomial functions. This unit, rational functions. Okay, so we're going to have polynomials in the numerator and denominator. So if you think back to the parent, this is our parent. This is our parent rational or reciprocal function. I could substitute in different values of x, but looking at the parent, what do you notice? You notice that there is a specific x value that will cause this to be undefined. What is that x value? 0. When x is 0, this is undefined. Everywhere else, I could go ahead and evaluate this function for any value of x. It kind of does. So I could evaluate this. We've done this already. And if you remember, we said it was undefined when x is equal to 0. The function is not defined there. But we had two little arms of this function, right? So if I plotted these points, in particular, if I plotted these, what quadrant am I in?
2. No, 3.
Both values are negative. I'm in the third quadrant, right? I'm in quadrant 3.
Because like as you get closer to 0, the y value goes.
Well, it depends which way you're approaching it, right? So it's going to look like this here. And then as soon as I get to the other side of x equals 0, I'm where?
Going up the other way. It's like the opposite. It goes like this.
I know what it looks like, but I love that you know what it looks like. I love it.
I don't know, weird like cross. I don't know how to describe it. Is there a word to describe it? Like,
It approaches the axes, but it never crosses it. So not only is this undefined, this vertical line is undefined, but also the x-axis is undefined. So this is going to bring us into what are known as vertical asymptotes, and we'll define these in detail next week. But I have a vertical, what's known as a vertical asymptote. At x equals 0, that's the equation of a vertical line. And I have what's also known as a horizontal asymptote the x-axis, which would be the equation what? What's the equation for the x-axis? Beautiful, thank you, Miles.
What's that?
So we're going to talk about that in detail next week. It is going to be a line or a curve that your graph approaches but doesn't necessarily cross in some instances. We will greatly elaborate on this next week, but I just wanted to give you an idea, a little foreshadowing. Now, with this parent function, we can describe the domain, the range, and the symmetry. So knowing what I know, that I never cross the y-axis for the parent rational functions and I never cross the x-axis for the parent rational function, tell me what the domain is in interval form.
Open interval negative infinity. Still, and then 0, but 0 is not included. Union 0, not included. Infinity.
Beautiful, Josh. And what about the range?
The range is, oh, it's the same thing.
It is.
It's the, but that's a horizontal asymptote instead of a vertical.
Yeah.
Oh, I see.
So is this even, odd, or neither? Well, remember, to show that it is even, I would have to show this. To show that it is odd, I would have to show this. Some of you on the test didn't really explicitly say what you were showing me. Can you tell me what it is? What? You can't be both.
Odd is
Verify it algebraically.
I don't know how to do that.
Yes, you do. Oh my gosh. Yes, you
I
do.
got that one wrong in the test.
It's odd.
Okay, let's do it. F of x is 1 over x. F of negative x is 1 over negative x. Are those the same? No. Come on now. 1 over x equals negative 1 over negative x. Look what happens there. Minus a minus becomes, it is odd. Uh-huh. Pitiful. Pitiful.
Oh, Dr. P.
Yes.
I figured out how to test both in one try.
I love it.
There's a way to test both in one try.
Yeah, sometimes make excuses.
I don't know why you're talking. You got all these problems here. Can you do these problems so we can go over them before you leave today? Because we're not coming back. We're moving on. Next week is all about graphing on Monday and Wednesday. No, what's Monday and Tuesday? What am I saying? Monday and Tuesday, and then your test is Thursday. We're working these problems. All the problems we skipped in the packet. You do them right now. Hey, it's your call. You do what you want. But, you know, I give you what I give you so that you can make an A. So it's your call what you choose to do.
Probably why his work's great.
Let's just put it this way. If it were me, I would do every single problem.
What did you pick? I don't even know.
I'm sorry, Shreyas. I think I may have thrown it in there because I cut out variation.
It's kind of sad.
I had to do another change because we switched. Okay. Are you okay with what we did?
Unless you take an AP class every semester of every class. So.
What are you saying, Josh?
You can't have a 5.0 if you take one.
Josh